Hi, everyone. I hope that you're all doing well. In this lecture, I want to show you an alternative perspective on the geometry of correlation. It's very insightful both in its own right, and it also helps make the connection to how we do statistics at higher levels, where the notation of matrix algebra is ubiquitous. It's in many ways an inverse to the traditional way that we think about correlation. So correlation is a little bit hard to directly visualize, but it's closely related to the technique of regression. In fact, in the bivariate setting that you're probably most familiar with, if you're watching this, the correlation coefficient and for two variables and the regression slope are just scalar multiples of one another, and we can kind of represent that like this. So in the traditional setting, we think about this is representing some variable x1, this is representing some variable x2, and we have some kind of cloud of points. And if we have a high correlation between the two, we might have something like this. And then we draw the regression line. I'll draw it in red here. That would appear to minimize the sum of squared distances from this line. I'm not a very good artist, so it's only approximate. But this is the traditional way that we think about the geometry of correlation. And in this video, I'm going to show you an alternative that's very powerful. And I'll explain the alternative in a moment, but I just first want to show you or remind you of a rule from high school geometry that's very useful. And it's maybe one that you never saw proved before, and it may not be one that you used very often, but it's one that's surprisingly easy to derive. And the name of this property is the law of cosines. There are alternative names for it. I believe I was doing a little research for this video that in France, for instance, it's given a name after the original author, much like we refer to the Pythagorean theorem in English. But generally speaking, I'll refer to it as the law of cosines. And it's a law that is not in its stated form immediately obvious why it might be interesting, as unfortunately certain parts of math just are initially not immediately exciting, but with the right explanation, they can become very exciting. So I want to draw it for you first, and then I'll explain why it's so cool. So you might remember from high school geometry that the Pythagorean theorem and a whole lot of pieces of what is known as trigonometry, so sine, cosine, and tangent, works best when you've got a right triangle. And so you've got a right triangle, you've got something like this, and you probably recall that this angle here is a 90-degree angle, and we'll use degrees rather than radians in this video. And this is this therefore makes a right triangle. And you've got, for instance, the cosine of some angle theta here. In this case, is pretty easy to define. If you've got here relative to this angle, the adjacent, the hypotenuse, and the opposite, cosine of theta is equal to the adjacent over the hypotenuse. The sine of theta is equal to the opposite over the hypotenuse. Let's make this a little clearer so it's not a 4. And that looks very messy. We'll try this one more time. You'll generally have to forgive my handwriting. And the tangent of theta is equal to the opposite over the adjacent. You may have you may recall a kind of catchy acronym for that called SOHCAHTOA that helps you remember how all of these things work, but very often in high school geometry, we just sort of leave things there. So you may wonder, how could I use trigonometry for an example like this one here? So trig, question mark, does trig work here? And it turns out that it does, but we need to derive really quickly a kind of better way, well, a way that actually just works in this case for expressing the relationship between angles and sides. So a very cool trick in geometry that we can often use is to, when we have a triangle that is not a right triangle, we can always split it into a right triangle by dropping a perpendicular right here. I'm only going to draw this one kind of right angle symbol here, but this forms two right angles since we're dropping this line directly perpendicular here. So we're splitting the 180-degree angle defined by the line into two 90-degree angles. So now we've got two right triangles here. Let's go ahead and label our sides. I'm actually going to do a couple of quick things first. So this is the height of two triangles. So I'm going to denote that h. And let's go ahead and define our sides. And let's actually just call this side x1. You'll see why in a moment, well, in a few moments. And let's call this side x2. And we can just call this side z. Now we also need to give names to these two sides that we formed by making up the triangle. So we'll go ahead and call this one here A, and we'll call this one here B. And switch back to black, and let's make it clear. Sorry about that. Make it clear that x1 refers to this entire thing, and A and B just refer to the segments. Okay, so now we need to define the angles that we're working with. And for now, we're just going to define this one here, and we can just call this one angle Z as well. And it'll be clear from context which one I'm referring to. So let's go ahead and see if we can somehow express a relationship here in terms of all of these factors that we just defined. So this might seem a little bit unmotivated at first, but I will show you where we're going in a moment. Our general goal is going to be to figure out how we can relate the cosine of an angle, or how we can define the cosine of an angle, say this one here, z. So we'll write out our task, find cosine of z in terms of x2, x1. I wrote these a little out of order. Just like we could in right triangle trig. So let's go ahead and take our first step. And our first step is going to seem somewhat counterintuitive, but what I'm going to do here is actually define this z here. And it's maybe a little bit confusing, I know, to have angle z and side z. It is conventional, however, to, generally speaking, refer to angles that oppose sides with the same notation, or to use Greek and Roman equivalents. But I found that using Greek letters is best done only when necessary, or utterly conventional, as in the case of theta up here. So we'll just go ahead and, again, try to keep that in mind. So how can we figure out the measure, say, of side z? Well, that's pretty easy, because that happens to be a right triangle. And so the Pythagorean theorem applies directly. And we can find the actual length of z here by taking the root of the left-hand side, but we don't need to do that directly in this case. So now I want you to do something kind of interesting. I want you to imagine rewriting b in terms of x and a. So let's swap that out, and we're going to, right here, kind of draw this here, write this out as it is x minus a squared plus h squared equals z squared. And let's put these midway marks here so that it's clear that this is not a 2, since I do have very sloppy handwriting. Okay, so what is our next step? Well, what we want to do is binomially expand this here, or do this binomial expansion, is maybe a clear way of saying that. So we're going to write out x squared minus 2ax plus a squared plus h squared equals z squared. And if that part didn't make sense, I would recommend, at that point, I don't have time to get into the reason for that. Binomial expansion is a pretty cool thing. Really, it may be most useful to go look at some geometric intuitions for why the distributive property works in the first place, which is a good thing to feel confident about when you're getting into higher math like this. So now we're going to do something kind of interesting, because what I want you to also note is that, and let's write it up here, even though we don't really need to write it, but might as well note a squared plus h squared equals x2 squared. So now let's see if we can find those properties, or those items in here. And I realized I forgot to write in here because I'm using x twice. This is x1. So that's important to note here. Okay. So can we find that information in here? And we actually can. So notice that this and this are equal to x2 squared. So we'll say x2 squared. And then we can kind of do a little bit of regrouping here. We've got x1 squared plus x2 squared. So we're getting pretty close to our goal here. But then we've got this minus 2a x1 equals z squared. And this a here is kind of unfortunate because it's a subset of x1. It's not a length that is related to the original sides directly, and depending on where and how we drew the non-right triangle here, that might be hard to define. So it would be nice if we could just somehow re-express that in terms of the original side. And we actually can do that because notice that A is also equal to the adjacent of this triangle up here. This guy, I probably need to be able to somehow point without making marks, but I'll just do this. This triangle here, it is the adjacent. So we can re-express that in terms of the cosine. So let's also make another note here. And conveniently, I didn't plan this, but A is the adjacent. So how can we then express that? Well, if the cosine of z here is equal to A over h, that means that we can then write h times cosine of z is equal to A. So this is kind of a nice property here because note that in this context, h is simply x2. So we can rewrite that as this here. So we have in finality we say that the z squared up here is equal to not x1 plus x1 squared plus x2 squared alone, but the two of them minus 2 times x1 times x2 times the cosine of the angle between them. So that is the law of cosines. Now, what does any of this have to do with statistics? Well, it turns out a lot. So what I want to show you now is a way of thinking about space in probably a very different way than the way you may have conceived of it before that turns out to be also very useful. So remember before that we had our picture, and I'll scroll back up so you can see it, of a scatter plot here. So this is what we call variable space. And note that what this kind of term indicates is that the dimensions of the space, so we've got, in this case, a two-dimensional space. Here's our first dimension. Here's our second dimension. These basically refer to the variables that you might use in a statistical analysis. So the dimensions of the space correspond to variables. But we can also think about what's known as subject space. And in subject space, which is kind of implicitly what we were looking at before, but I want to make it explicit. In subject space, and I'm going to draw 3 dimensions here for full effect. This would be person 1. Let's call them subject 1 just to be clearest. This is also sometimes known as observation space. And the assignment here doesn't really matter too much. we could make this subject 2 down here and this subject 1 up here, no difference made. But the principle is that, and by the way, the z direction here will also be subject 3. The principle is that the dimensions of the space correspond to individuals. And it might seem really unclear why you would want to do that, but it's because it actually makes the geometry of correlation a little bit different, but very, very interesting to examine. So let's draw some vectors in here. And remember that vectors are basically, you can think about them in many different ways, but they're just points in coordinate space. They end typically in arrows in the traditional way of defining them or showing them, really not defining them. But fundamentally, vectors are just also lists of numbers that can be thought of as the coordinates in n-dimensional space. And if that scares you a little bit, just think about it as, say, 2-dimensional space, or in this case, 3-dimensional space. So what I could do here is actually represent one of the variables, or the realizations on that variable to be most exact, as a vector x1. And x1 would have coordinates x1, 1, right? And then x1, 2. And which one of those subscripts goes first will change depending on context. I'm just doing it in this fashion here, and then here x1, 3. So you can think about writing out the vector as basically this list of coordinates. So x1 would be defined by subject 1's score on the variable, and then subject 2's score on the variable, and then subject 3's score on the variable. And these are scores on variables. Well, just a variable here. But also coordinates in 3-dimensional space. And I'm going to show the standard way of writing n-dimensional space here. So you'll note that, sorry, I'm trying to zoom in. You'll note here, let's make that a little bit more obvious, that this blackboard bold R with an exponent looking thing here, we should really call it a superscript to be most exact, is the way that we note n-dimensional space, or in this case, 3-dimensional space. So we say R3. Then also note, however, that we had 2 variables. And let's say that the other set of variables produces a score, or a score vector, that kind of comes out here. And let's say that this is x2. And what you might notice is that there is a relationship between these 2 vectors. And this offers another way to see the relationship between 2 variables, except now we are no longer in variable space with the variation on each variable represented by the scatter of points on one dimension, the other, and then their conjunction. In this case, we're actually going to think about the relationship between variables as being given by a couple of different things, but primarily how close the vectors are to each other in terms of the angle between them. So one thing to note here, an important fact from linear algebra, is that if you have 2 vectors, even if those vectors are themselves in a high dimension space, so one thing that you might be wondering about right away is, well, there's typically more than 3 subjects in a data set. How does this generalize? I'll come back to that, but the point is you have to start thinking about it in sort of, abstract and analogy, or an analogical thinking, I guess. I'm not sure how to say that exactly. Not analogous, but you have to think it's sort of a kind of an analogy is what I mean to say. But the intuition generalizes. Another point, though, that's kind of important is that if you have just 2 vectors, those just span a single plane. So in other words, if you imagine taking, say, this vector here, and then putting it tip to tail with this vector here, you'll note that all the combinations we can form by, say, stretching this out in this direction or stretching it in the opposite direction, etc., you'll note that all of those are just actually spanning a plane. And it may not be obvious from the way I drew that. So let me kind of show that maybe a little bit better here. So the idea is that when you add two vectors, you just put them tip to tail, and that corresponds geometrically to adding up all of the corresponding coordinates. But when you're just adding a scalar multiple here, notice that all of the points that I can reach by, say, adding a multiplication of x1 to x2, that all the points I can reach here just happen to lie along a plane, and that's true even if I go in the opposite direction. So let's undo all that and keep this where it was. So that means that the vectors, even if they're in a high dimension space, have a well-defined angle between them that is basically like a plane or Cartesian space that is a subset, pardon me, of this space that the vectors actually lie in, or I should say most properly, it's a lower dimensional space than the one the vectors lie in. And so we can actually go ahead and come back to the simple picture that we had before, just in two-dimensional space. And let's actually pull that up, and we'll just copy it down here. So I'm going to show you just one more trick. Oops, I'll come here. I'm going to show just one more trick because this is almost the trick, but we need to do something with z. So remember that our law of cosines right here tells us that x1 squared plus x2 squared minus 2 times the product of them times the cosine of z is equal to z squared. So this, remember, is our picture. But then let's notice something here. So remember that I defined z a little bit ago, or I told you just a little bit ago, that by going from, say, this vector here to this vector here, that you could think about that as, in a certain sense, addition. So if you think about replacing that z with the basically correct linear algebraic expression, what you're doing is figuring out, you're basically saying what quantity goes from x2 to x1 here. So this is actually just x2 minus x1. That's what we can replace z with. And I'll enclose it in parentheses here, even though we don't, strictly speaking, need to do that. And the reason is that if we now think of these as vectors, and we can draw these little vector signs on here. So by definition, if this represents a vector addition, right, then what we're going to get here, oh, sorry, this should actually be, I flipped the subscripts here, but the point remains the same. So if we add x2 to x1 minus x2, we of course just get x1. And you can see here, and let's make this subscript again a little bit clearer. Just erase and retry. A few mistakes never hurt anyone. You can see that this follows our rules of vector addition, because when we add this quantity here to this quantity here, we do in fact get this quantity here, or x1. Okay, so let's go ahead and put our same law of cosines together, except now what we're going to do is write this a little bit more clearly, or more usefully. And let's actually start with the nonlinear algebraic expression, then I'll explain a little bit of linear algebra for you. So we're going to now say we've got x1 squared plus x2 squared minus 2 times x1 times x2 times the cosine. And let's just replace this now with the generic theta, because we no longer have a z, and this part we don't need to worry too much about. So we've just got a theta here, equals, and then now we're going to take what we had. So recall above that we had z squared there. We're going to say x1 minus x2 squared. And one of the reasons that I made that small goof earlier is that when we square this quantity, it also isn't going to matter which we subtract. But for the sake of explaining why I can replace z with x1 minus x2, it's probably useful to know the correct expression. Okay, so now we have a nice way to express this, but the problem is that this is in 2 dimensions. And so now we need to just think about a really cool fact that you probably could intuit, but may not have known, which is that the Pythagorean theorem actually applies in arbitrary dimensions. So in 3 dimensions, for instance, like let's just write this out here. So suppose we just have one of these vectors up here. Don't think about these as the vectors we've been using. Just think about it as a generic vector v, just so we don't get confused, since down here, the vectors are in 2 dimensions and up here they're in 3. So just think about it as one of these guys here is just representing some generic v. So the length of v, so if we think about the length of v, how can we define the length of the entire vector? So when we write vectors here, like when we're writing sides of a triangle like a, b, and c, we implicitly mean their magnitude, but vectors, generally speaking, mean coordinates. So when we define length, we actually write it like this. And you will see some authors just use single upper bars there, but since that, although it has a similar concept to absolute value, it's best to keep it distinct. I'll use double bars, which is also pretty common. And we're going to say that the same holds true. So the length of vector v squared is equal to the component parts squared. So v1, here the subscript means, again, the component. So the first component plus the second component squared, of course, just like in the Pythagorean theorem, plus the third component squared. Okay, so that's all well and good, and this extends generally, so I'll just say generically for some vector v in Rn, I want to keep using subscripts because that can get confusing. For vectors v in Rn, the length of v squared equals v1 squared plus vn squared. And I need to show just one final property here, or make one note, which is that in linear algebra, we can write this as what is known as a dot product. So a dot product of 2 vectors says multiply component-wise and sum. And I say component-wise because if you've had any encounter with linear algebra before, undoubtedly you've been kind of lectured on the fact that matrix multiplication is not as you might expect. So you know that matrices, the way that we multiply them, we generally don't multiply all the component parts together and then add or something like that. It's a little more complicated. There's some really good videos on the internet about that. I recommend very strongly the videos of Dr. Trevor Bassett. I'll write his name here. He spells it with an F, so just so you know, although I'm sure you could Google it and get the same thing, or the video series 3 Blue, 1 Brown. These are both excellent. So go check those out if you're interested in matrix multiplication. That's a pretty natural next step. But dot products actually kind of work a little bit more like you would expect. So they tell us for 2 vectors, you pair up all the component parts and then just sum them. So it hopefully seems pretty straightforward then that we can replace this expression on the right with a dot product. So this is equal to the vector dotted with itself. And we can write that using matrix multiplication. The way that we do that is we write that it's the transpose of the vector on the left here times the vector on the right. And actually, we don't need the dot anymore. Sorry about that. Since this is no longer a dot product, this is just matrix multiplication. And I, by the way, write transposes with a T rather than a prime because the prime is sort of overloaded notation. And we'll typically conceive of vectors in this video and in statistics generally as being column vectors unless otherwise noted. So just to show you that this matrix multiplication here works, it's technically vector multiplication, but that's a subset of matrix multiplication if you really think about it. So we've got here V1, V2, etc. And we'll just write this like this. Vn, and then we've got here v1, v2, vn. And the way that I like to think about matrix multiplication is that I use the linear combination method. So I think about this here on the left as a replacement for the standard set of basis vectors that are given by the identity matrix in the correct dimensions. And then I think about this vector here as giving a set of instructions. So here, the way we think about this is we take this vector, we kind of plop it on its side. So we have V1 here, and then we're going to do some stuff with it. V2 here, do some stuff with it. And then Vn here, do some stuff with it. And then what those are coefficients on are actually the columns of these here. Now here, these aren't actually columns. They're just scalars, but you can think about it as it would be correct if we had a bunch of junk down here. So then this is just multiplication, V1, V1 plus V2, V2 plus Vn, Vn. So that also is a dot product, but I just wanted to show you that. Again, if that linear combination approach to matrix multiplication seems a little bit unusual, or you learned, the typical way people are taught to memorize this is actually a different algorithm, which is useful in many contexts, but not really when you're first learning it, unfortunately. Go see those videos I recommended, and both of them give you a good reason to think about matrix multiplication in this fashion. Basically, you'll think about the left matrix as a transformation of the standard basis vectors, or the kind of standard directions you would go. So one in every distinct direction that you can go. So for instance, you would have some standard basis vectors here that would be 1, 0. Whoops, let's write this here. We'll change color. Your standard basis vectors here would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. And you can see those are kind of the cardinal directions. But you could think about any collection of 3 vectors that are each 3 items long as being different basis vectors. So they could be out here and out here and way out here if you want. And then you're just applying the, when you multiply some vector by that matrix, you're taking the instructions embedded in that vector and just applying them to new basis vectors. I think that's a really helpful and fun way to think about matrix multiplication. Okay, so let's come back to the main point. So why did I write all that out in the way that I did? Well, it's because we want to generalize the law of cosines to arbitrary dimensions. So first, we're seeing that it actually applies to the situation where the vectors represent variables, but then we need to deal with the complication that this could go into higher dimensions. So we're going to now finally replace these x's here with dot products representing their length. So now let's translate that into vector notation. So we're going to write the length of the x1 vector squared, the squared length of it, I should say, like this, as before. And then we'll do the same thing for the x2 vector. And minus 2 times, this will just be the unsquared length of x1 times the unsquared length of x2 times the cosine, which doesn't change. And that is equal to then the squared length of the difference. I'll write this down here. And remember that using our rules from before, that can just be expressed as the dot product of the vector with itself, and that gets a little complicated because it's actually a difference in 2 vectors here. But it turns out, you may assume that this could be done, and in fact it can, that you can just distribute the dot product, and I left out the dot there. You may want to think about why that's the case. I'll show you briefly. So if you think about what the dot product is telling you, it's basically telling you to take the two vectors, and we could write this as really just like one fat difference vector here. It's just sort of notational, but hopefully gives you a sense of what's going on. So we're going to multiply these basically component-wise. So we'll just kind of represent that like this. And then basically this equals some vector of products. And then sum the entries. So if we kind of just pick a generic component here, say the x1 ith component minus the x2 ith component, the same is true here, then this would of course just be the binomial expansion in here. So we would just distribute like so when we do the multiplication operation for these two here. That was not a very coherent thing. So when we do that operation here, that just becomes binomial expansion like normal, or foiling. And then if we're just summing up all the entries at the end, we're just summing up a bunch of those binomial expansions. So then it turns out that allows us to distribute the dot product, because if we kind of come back up here and we think about what's going on, so we'll be summing up basically all of the x1 products. So we take xi, let's come back and do that correctly. So plus x1 I times x1 I plus x1 I plus 1 x1 I plus 1. My handwriting is getting terrible. Plus So that of course is just the dot product x1 and x1. And then notice then that we would have the same thing for every other kind of unique type of component. So that means that that's not a very rigorous proof, but hopefully that gives you an intuition for why you can distribute the dot product. So this is equal to x1 dotted with itself minus 2 x1 dotted with x2 plus x2 dotted with itself. So now let's recall conveniently that this here is equal to, from how we defined it before. So remember that we said this also gives the square length, the length of x squared. So conveniently, this is just equal to this. This is just equal to this. So notice here that we then have, let's change colors one more time. Let's go with this purple. So this gets knocked out here. This gets knocked out here. And then what are we left with? So we have, I'll keep this new color, negative 2 x1, and that is the length of x1 times the length of x2 is equal to negative 2 times x1. This should really be a dot here, dotted with x2. And this is very exciting. So one thing we can notice right away is that the negative 2's cancel. Oh, and there should be a cosine in there as well. Sorry, lots of moving parts. So cosine of theta. And we're almost there. So let's rewrite that. We can just divide out. So dividing the left-hand side by everything but cosine, and doing the same, of course, on the right-hand side, we have that the cosine of theta is equal to the dot product, the two vectors, over the product of their lengths. Now this is very, very cool. Why? So let's make one sort of final modification to the framework that we've been using. So far, remember that when I told you about subject space, I was telling you to think about basically the different axes as representing people. And so a vector represents a score in n dimensions or on n people. So now let's assume centered vectors. So what are centered vectors? What this means is that x1, let's say our new x1 equals basically x1. Let's write this slightly differently. Minus the mean. So in other words, we just take the mean of everyone, or we take the mean of the vector and then we take everyone's difference from it. So what that would look like in vector format is something like this. I'm using x bar notation here, x2 minus x bar and so on, xn minus x bar. Okay, so now we're going to assume our vectors are centered, and this is a very common operation. It's not a really crazy mathematical transformation, so hopefully it doesn't sound too wild to assume this. And in fact, otherwise what I'm showing you won't really work. So now if we assume that our vectors are centered, what do we have going on here? So it turns out to be pretty cool, because if we copy this down, like this, now notice that these are actually centered. So what we have here, and let's rewrite the dot product in a more familiar form, in summation notation. So what this is the centered vector. So since we are writing this out as a sum, we can use subscript notation. And let's write this a little more carefully with the 1 here. Wait, we don't need vector notation here. Sorry. It's been a long video. My brain's getting a little tired. Probably should have used X and Y, but I try not to do that because then that tends to confuse people that are thinking about space in a new way, and I'd rather just use these different notations. And then now what we have in the denominator is basically this. So we've, in this case, just got the roots of these sums of squares. I won't write out the exact index notation here, but it's basically this. And we'll do an asterisk to make it clear that we're no longer thinking about dot products or anything like that here. Now this is very cool because hopefully you recognize this as the correlation formula. If you've seen it in another form before, like let's say you may have seen it as the standardized covariance. So this is the correlation. Maybe you've seen it though in this other form. So just let's check our intuition, or check with our intuition. So it's covariance of x1 and x2 over standard deviation of x1 times the standard deviation of x2. So we standardize the covariance. So this equals basically this bit from the top up here. I'll just copy it down because it's kind of a lot to write. Except now divided by n minus 1 this video. We do not have time to get into the Bessel correction, so forgive me. Although, actually, quite interestingly, this follows very naturally from the geometry. And then the standard deviations of our two variables. Almost everything in statistics becomes easier with the geometry. So we come here, except now we have to do a little bit of cleanup, although you'll see that soon enough this becomes somewhat superfluous. It's a terrible radical sign, but close enough. Now, a little bit of kind of high school algebra should remind you that when you multiply together these two things that share an exponent, you can just turn that into one entire thing that shares an exponent. So I'll walk through that, I guess it might as well. So the denominator, we'll just say the denominator becomes this. So we've got the entire thing right here. Actually, there's a couple of ways to do this. Let's do it like this. Let's make it simpler. This is a simpler approach. So we can actually just delete this here. Basically, you can also factor top and bottom into square roots here. So we have, let's just call this the total sum of the squares of x1 for simplicity. Means the same thing, times the total sum of squares of x2 for simplicity over root n minus 1 over root n minus 1. So when we do this together, we then get equals the product of those two things. I'll just write that like this, over n minus 1. So now those n minus 1s will cancel. Let's use our kind of standard cancellation notation from above. So just like this and like this. And then we just have basically the top of the covariance divided by the top of the standard deviation. And you'll see that what that ends up being is the, if I can switch my notation here, the sum of the co-deviation products, or the deviation products, if you like, over the product of the sums of squares, which is this way of writing the correlation formula up here, which you'll notice is just how we write what we found from before, but not with the notation of linear algebra, but instead just with summation notation. So this is a very cool fact, and let's kind of bring it back to the very start, and we'll draw just one more picture. So what this means is that the cosine of the angle between our two vectors here so the cosine of theta, which is just a kind of familiar trigonometric function of theta, is equal to the correlation coefficient of centered x1 and x2. What that means is that you can understand the correlation coefficient as basically how angularly close these two variables are when they're turned into vectors in n dimensions. And maybe the most kind of obvious and useful payoff is that you probably remember from high school geometry or trigonometry that the cosine of any angle is bounded between -1 and 1 inclusive. And this is a fact that most people don't find too hard to memorize, but they might not know why it is, or they might have some kind of vague intuition that it has to do with the standardization, which is true from another angle. But one very nice way to see the fact that the correlation coefficient varies between -1 and 1 inclusive, write the sample Pearson correlation coefficient using the standard notation of lowercase r. So it should be a kind of italicized r, I guess. What that means is that that's another explanation for why the correlation coefficient always varies between -1 and 1 inclusive. So I'll stop there. I'll probably update this lecture series with another example of how the geometry of regression or correlation, I'm thinking ahead, I'll probably update it with how in general, these operations here of assessing the relationship between quantitative variables can be understood in a meaningful and deep way by considering them through a linear algebraic lens. I hope this has been helpful, and thank you for watching.